Okay, so we can now move on to chapter 4, where I am going to apply everything we have learned in chapter 3, and so that everybody knows why we need all of this stuff. Why do we need the rate of change? Why do we need all of that? We are going to learn that here. We are going to start with section 4.1, related rates. So let me first say what a related rate is, okay? So this is whenever two things are going to change together, okay? They may not change at the same rate, but they are going to change at the same time, okay? So an example of that is if I have like a ladder leaned up against a wall. So let's say I have a wall and the floor and a ladder right here, and the ladder starts to fall down, okay? When the ladder starts to slide down, my height is going to change, right? Because it's going to slide down. Well, at the same time, how far away I am from the wall is going to change too. Because as I fall down, I'm going to slide out. So those are related rates because they are going to change at the same time, okay? Notice, though, the ladder length is a constant, right? And so that's not a rate because it's a constant, okay? So, but this is what I want to do here. I want to look at two things that are going to change at the same time. And then I just said two things, but I could have a lot of things, okay? But things that are going to change at the same time. So, example here, a spherical balloon is being filled with air at a constant rate of 2 cubic centimeters per second. How fast is the radius increasing when the radius is 3 centimeters? Hint, the volume is V equals 4/3 pi r to the third. Okay, so think about what is being changed here. So as I'm going to blow in the air, right, I'm changing the volume, right? Well, as I'm increasing that, as it's blowing up, I'm trying to show you with my hands, but I'm very zoomed in. As I'm increasing, it's going to grow and grow and grow, right? Well, not only does the volume increase, but so does the R, right? Because if I start out pretty small, and then I blow in air, it's going to grow, so R will grow. And then I do more, it's going to grow even more, R will grow too. So V and R are going to both change, okay? Since these are rates of change, we learned in chapter 3 that is the derivative. So to figure out what the rates are, I have to find what the derivatives are. So that's what I want to do now. The derivative of V is just a 1, right? But V is going to change, and so I need the rate of change of V. So that's the change in V with respect to time. Okay, so dV dt, because V is going to change with time. Okay, equals, do the derivative of all of that side. Remember, 4/3 and pi are just constants, right? So I can just use the power rule here. Bring 3 down. 3 times 4/3 is just 4. Pi is just a constant, so that's going to just stay pi. And then since it was r to the third, go down by a 1, and that's r squared now. But remember we said r is going to change, right? Because as I grow, r is going to change. So I have to multiply that by dr dt by the chain rule, right? Because r depends on time. So this is what I get. dv dt is equal to 4 pi r squared dr dt. Again, I have to times this by dr dt because r is going to change with time. So now I'm going to read all of this and be like, okay, what parts do I know and what do I need to solve for? So I know my change in volume is going to be 2. So I know dv dt is 2 because that's what they said at the start, right? And so what it wants to know is how fast does r grow? So they want dr dt when r is equal to 3. So now I know r is equal to 3. So now I can plug in everything that I know. dv dt is 2 equals 4 pi, and I know r is 3. dr dt. So now I just have to solve this for dr dt. 3 squared, I get 9. 9 times 4 is 36. So to get dr dt, you just have to divide by 36 pi. 2 over 36 is 1 over 18. So that's 1 over 18 pi. The radius is in centimeters, so that is centimeters per second. Again, so what I did right here was I wrote what the formula is, and then I took the derivative of that, and then solved it for dr dt. This next part asks, what is the instantaneous rate of change of r when r is equal to 6? So the good thing is we already have a good start, right? We already know from the first one that dv dt is equal to 4 pi r squared dr dt. So now I just have to instead plug in a 6 for r. So dv dt, we already know is 2. 4 pi r is now 6 squared dr dt. And I just have to solve that now. So 6 squared is 36. 36 times 4 is 144. So that becomes 2 equals 144 pi times dr dt. So we just have to divide by 144 pi. 2 over 144 is 1 over 72. So this becomes 1 over 72 pi is dr dt. And there we go. Let's see if we can do a different example using the same kind of thought. Okay? An airplane is flying overhead at a constant elevation of 4,000 feet. A man is viewing the plane from a position 3,000 feet from the base. The airplane is flying horizontally away from the man. If the plane is flying at a rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? Okay, so there's a lot happening. Okay, what we know for sure is that there's a man. I'm trying to leave plenty of space here. What we know for sure is that there's a man and there's a plane. Watch my art skills here. Oh, yeah. There we go. There's a plane. Ooh, that's horrible. Anyway, the plane is flying this way. Okay? And that's what we know. We also know that the height of the plane is always 4,000 feet. And what we want to know is the rate of change from the man to the plane. So what I can do here is I can actually make a right triangle and use that to figure everything out. Okay. So the distance between the man and the plane is not a constant because this plane is flying, right? It's flying, flying, flying. So this length right here is not a constant. Therefore, let's just name that, I don't know, let's just name it an x. Well, since this length is not constant, neither is the hypotenuse, right? So the hypotenuse, let's just name that a y. It doesn't matter, though. I could use a and b, I could use L and h. It doesn't matter. I just picked x, y. So now I've got to think, okay, what equation can I make from this? Okay, well, this is a right triangle, and so I can use the Pythagorean theorem to write an equation. And remember that says a squared plus b squared is equal to the hypotenuse squared. So in this case, I have x squared plus, this is a constant, 4,000, it's always that height, is equal to y squared. 4,000 squared is 16 with 6 zeros. Y squared. So now x and y are going to change, and so I need to find what the rates of change are, right? And therefore, I need to find what the derivative is. The derivative of x squared is 2x, but since x is going to change, right, because this is going up, I need to multiply that by dx dt. The derivative of this is going to be equal to 0, so I can just leave that out. And then the derivative of y squared is 2y, but since y is going to change, I need to multiply that by dy dt. So now plug in what I know, okay? At this particular point, we are trying to say that the plane is flying over the tower. Well, it said a while ago that the man is 3,000 feet away from the tower. Therefore, there's 3,000 feet right here at that specific time. So x is going to be 3,000. dx dt is going to be the speed at which I'm going to change right here, right? Well, the plane is flying, and so the rate of change of this side is the same as the speed of the plane, which we said was, there it is, 600 feet per second. So dx dt is 600. Now, it's wanting to know the rate of change from the man to the plane. So it wants the rate of change of this side, which is dy dt. So since I'm solving for dy dt, I have to plug something in there for the y. Well, the good thing is I already have an equation right here on how x relates to the y. So since I know what it is for x, I can use that and get what the y is. So at this specific point, we know x is 3,000. So 3,000 squared plus 16 million, I think is what that number is, equals y squared. And I can solve this for the y. So I know 3,000 squared is going to be 9 million plus 16 million. Is y squared. So to figure out what the y is, just take the square root of that, which you would see is 5,000. So y at this time is equal to 5,000. So now I can plug all of this in to figure out what dy dt is. So that's 2 times x, which is 3,000, times dx dt, which is 600, is equal to 2 times y, so 2 times 5,000, times dy dt. 2 times 3,000 times 600 is, I hate reading numbers out loud, 3,600,000, I believe is correct. 1, 2, 3, 4, 5 equals 2 times 5,000 is 10,000. So just divide by 10,000. And for dy dt, you get 360. So this length right here is going to change by 360 feet per second. Again, what we did there was I know these terms relate, and so I'm going to write a formula for how they do that, and then take the derivative and plug in what I know so that I can solve for what I don't know. Looking at another example, this one actually says in the example above, what is the speed of the plane if the distance between the person and the plane increases at a rate of 300. So for this one, everything is the same thing. So we still have what we said over here. 2x dx dt equals 2y dy dt. We still have that. And we still have, it doesn't change anything else, so we still know that x is equal to 3,000, and we solved for y equals 5,000. But this time it's saying we know what dy dt is, and we are saying that is 300. So now I'm going to use all of that to solve for dx dt. So 2 times x, which we said was 3,000, dx dt is what I don't know, was 2 times y, which we said was 5,000, times dy dt, which is 300. Cutting that a little close, so sorry about that. 2 times 3,000 is 6,000. 2 times 5,000 is 10,000. 10,000 times 300 is, I know it's going to have a 3 at the front, but like I said, I always mess up the numbers, like the names of them. 3 million. Divide by 6,000, and you get 500. And again, this is in feet per second. So for this one, we just used the same thing. We just had to pull, again, a dy dt and solve it for dx dt. All right, moving on to the next one. A rocket is launched so that it rises vertically. A camera is positioned 5,000 feet from the launch pad. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Find the necessary rate of change of the camera's angle as the function of time so that it stays focused. So let's draw that one out. I have a camera right here, and it's pointing to a platform, and the rocket is going to launch up. So again, just like our last one, we can make a right triangle with it like this. Now, reading this, the only thing that's constant is how far I am from the camera to the platform, which is 5,000 feet. Everything else is not constant. And I'm going to read that. Sorry. In here, we have what the height is, and so let's worry about height. Let's call this an x. And then it asks for the angle. So we're going to talk about the angle right here. So when I think about what equation I can make from that, notice I have this side and this side over here. I have the opposite side and the adjacent side. That is tangent. So I have tangent of theta equals x over 5,000. So again, now I'm looking at the rates, and so that I need to take the derivatives of all of this stuff. Okay, the derivative of tangent is secant squared, so secant squared theta. But since theta is going to change with time, I need to multiply that by d theta dt is equal to the derivative of x over 5,000 is just 1 over 5,000 because the derivative of x is a 1. But since x does change with time, we need to multiply that by dx dt. And so now I need to plug in everything I know so that I can solve for what I don't know. They want the rate of change for the angle, and therefore what they want us to solve for is d theta dt. So I need something for everything else. Okay. Theta first. Remember, we know theta. We know the tangent of it is equal to x over 5,000. So I want to know is what theta is at this certain time. Well, they are saying when the height of it is 1,000. So x is equal to 1,000. So they want to know tangent theta of 1,000 over 5,000. Well, I can reduce this to be 1 over 5. 1 over 5. So if I'm looking at tangent of theta is equal to 1 over 5, this means that the opposite side is going to be 1. The adjacent side is going to be a 5. Okay. So what I really want is secant squared of that. So I have to first find out what the secant is here. Well, secant is hypotenuse over adjacent. So I need to know what the hypotenuse is. To get that, we know the hypotenuse squared is equal to 5 squared plus 1 squared. 5 squared is 26. 1 squared, or 25, sorry, I got ahead of myself. 25, 1 squared is 1. So h squared is equal to 26. So the hypotenuse is the square root of 26. So we know the secant of theta is square root of 26 over 5. So since it wants secant squared, I just square that. So secant squared is going to be square root of 26 squared is just 26 over 5 squared is 25. d theta dt is what I want to solve for. Equals 1 over 5,000. And the rate of change of the height, they already said, is 600. So now I just have to solve this for d theta dt. 600 over 5,000, we can reduce that. 6 over 50 is like saying 3 over 25. So 26 over 25 d theta dt is equal to 3 over 25. To solve for d theta dt, multiply by 25 over 26 to cancel it out. 25's cancel out. So d theta dt is equal to 3 over 26. And since this is the theta, this is radians per second. So the hardest part here was because they wanted secant squared, and so I needed to first find what that was, right? That was really the hard part here. Everything else is still just find what the rate is, and then plug in what I know to solve for what I don't know. Okay, it's the same thing. Looking at this next example, what rate of change would we need for the elevation angle of the camera if the camera is placed on the ground at a distance of 4,000 feet and the velocity is 500 feet per second when the rocket is 2,000 feet from the ground? So everything is the same here. It's just changing what the numbers are. Okay. So it's going to work the same way. It'll still be secant squared theta d theta dt equals, now since this length is 4,000 feet, it's going to be 1 over 4,000 dx dt. So now they are saying dx dt, the velocity is 500. So I still need to know, that since 5,000, I'm at 500, what secant squared is. So what I know so far is that on theta, we know the height is 2,000, and we are 4,000 away. So tangent of theta, oh, sorry, I need secant, so sorry. We need secant, so I need this side length right here. So we would do hypotenuse squared is 4,000 squared plus 2,000 squared. If I typed in 4,000 squared plus 2,000 squared, you get 20 million. Take the square root of that, and you get h equals the square root of 20 million. 1, 2, 3, 4, 5, 6. And we can factor out a million. Just because this is a whole mess, we can write that as the square root of 20 times a million. And the square root of a million is 1,000. Square roots of 20. That's way better. 1,000 square roots of 20. So secant of theta for this one would be 1,000 square roots of 20 over 4,000. Reduce that. and you get 1 over 4, so square root of 20 over 4. But they want secant squared. Square root of 20 squared is 20 over 4 squared, which is 16. And we can reduce that down to be 5 over 4. So secant squared is 5 over 4. d theta dt is what we want, so leave it. 1 over 4,000. And like we said, dx dt is now 500. Excuse me. So now solve this for d theta dt. Let's reduce this fraction over here. 500 over 4,000 gives us 1 over 8. So when we multiply by 4/5 to cancel it out, 4 over 8 cancel out to give me 1 over 2. So I have 1 over 2 times 5 is 10 radians per second. So once again, the hardest part here is just finding what secant squared is. Everything else is just plugging in stuff. Few more examples. This one is fun. I really enjoy this next example. I hope you guys do too. Water is draining from the bottom of a cone-shaped funnel at a rate of 0.03 cubic feet per second. The height of the funnel is 2 feet, and the radius at the top of it is 1 foot. At what rate is the height of the water changing when the height of it is 1/2 of a foot? Hint, the volume of the cone is V equals 1/3 pi r squared times h. So let's draw all of this out. So we have a cone-shaped funnel. I'm going to try to draw my best cone I can right here. I know the height of the whole thing is 2 feet. And we know the radius of the whole thing is 1 foot. But I know that inside of here we have some water, and I'm draining that out of there, right? So what I want to know is the rate of change of the water, not of the cone, right? Of the water. So I need to figure out what h is and what r is at any time there. So what I want is to either write r in terms of the h or write h in terms of the r, okay? Well, since they tell us what the height of the water is, it would be nice if everything was in terms of an h. So I want to write this r in terms of the h. So let's see how I can do that. Well, if you look, I can make this 2 similar triangles and figure out what happens there, okay? So I know radius relates to the height as the same way r for the whole thing was 1 and height for the whole thing was 2. So how those two relate should be the same thing. So I should be able to cross multiply these and get to the same thing. So r times 2 is 2r, h times 1 is h. So solving this for r, we can just divide by 2, and we see r is equal to h over 2. So when I'm writing this guy right here, instead of r, I can replace that with h over 2. So volume is equal to 1/3 pi h over 2 squared times h. We can simplify this. H over 2 squared is h squared over 4, because 2 squared is 4, times h. So volume is equal to, down here I have 3 times 4, so that's 12. So I have pi over 12, h squared times h is h to the 3rd. Again, this only works in this case I have here. This isn't always true for all cones, okay? It only works here. So now I want to deal with rates of change. So now I have to take the derivative of all of this stuff. The rate of change of v, the volume is changing with time, so dv dt. Pi over 12 is a constant, so we'll just bring 3 down. 3 times pi over 12 is pi over 4 times h. My power was a 3, now it's 2. But my height is going to change with time, So dh dt. They want to know what the rate of change is for the height, and so they want dh dt. So I need something to plug in for dv dt. Well, it says the volume is going to pour out at a rate of 0.03. Since it's pouring out, my rate of change is negative because it's going to pour out. And then I need something for the height, and we said right here our height is 1/2. So I can plug everything in. Negative 0.03 equals pi over 4 times 1/2 squared dh dt. 1/2 squared is 1 over 4. 1 over 4 times pi over 4 is pi over 16 times dh. So to get dh dt, we just need to multiply by 16 over pi. Negative 0.03 times 16 is negative 0.48. So that's negative 0.48 over pi is dh dt. Again, this is just about plugging in things that I know to find things that I don't know. And since these are rates, we take the derivative. This last one right here, at what rate is the height of the water changing when the height is 1 over 4? So again, everything is the same thing. We already have dv dt equals pi over 4 h squared dh dt. They want to know what the rate of change is for the height, which is dh dt, except now my height I'm going to use as 1 over 4 instead of 1/2. So everything else is the same thing. So still negative 0.03 equals pi over 4 times 1 over 4 squared. 1 over 4 squared is 1 over 16. 1 over 16 times pi over 4 is pi over 64. So to solve this for dh dt, just multiply it by 64 over pi. Negative 0.03 times 64 is negative. Oh, sorry, I did not notice that was on top of the camera. There we go.